Good morning and welcome to this class. Today we are going to discuss about the electric field due to infinite length line charge. And we are going to obtain the electric field intensity in cylindrical coordinates. That means basically in terms of rho, phi and z. Suppose you have a line charge extending from, let us say, z is equal to minus infinity to z is equal to plus infinity. Let rho L is the density, rho L coulombs per meter. At a given point P, what is the expression for the electric field intensity? Assume that the perpendicular distance from point P onto the line charge is rho meters. Okay. Now what I'm going to do is I'm going to divide this line charge into small segments, each of incremental length dl. So now the dl is represented as dz because it is placed along z-axis. So when you consider one such dz, this has got a charge of dq, which is given by rho L into dz. So forget about the remaining part of the line charge. When you consider only this dz, which has got a charge of rho L into dz, let r1 is the distance. Find out what is the differential electric field intensity at point P because of this dz. Then you consider another dz. Find out what is the electric field. Like that, another dz. Find out what is electric field. So when you consider all these differential electric field intensities obtained by various incremental lengths, and when you add all these differential values of electric field intensities, you get the total electric field. So that means we are applying the property of linearity in order to obtain the total electric field intensity. So mathematically, how we are going to do this? Because we know that integration is nothing but summation. So what I'm going to do is I'm going to consider a differential length dz at a distance of z meters above this z is equal to 0 plane. So let r is the distance from dz to point P. So the idea here is if you can find out what is the differential electric field at point P because of this dz, which has got a charge of rho L into dz, you get one expression. When you integrate that expression, you get the total electric field intensity. So electric field due to infinite length line charge, we want the expression in cylindrical coordinates. So now this is the infinite length line charge placed along z-axis, extending from z is equal to minus infinity to z is equal to plus infinity. So I'm considering a differential length dz at a distance of z meters above this z is equal to 0 plane, assuming that the line charge is placed along z-axis. Let r is the vectorial distance from dz to point P and the perpendicular distance from point P onto this line charge is rho. Okay. So dz means how much charge it has got, rho L into dz. Take this as a point charge. So what is the corresponding differential electric field at point P? What is the magnitude? Magnitude is given by dq, that is rho L into dz by 4 pi epsilon naught r square ar. Okay. What is ar? Along the direction of r. Vector r is directed from dz to point P. Now what all I have to do is, because I want an expression in cylindrical coordinates, I have to express r square and ar in cylindrical coordinates. So for this, if you look at this triangle, ZAZ plus vector R minus rho A rho is equal to 0. ZAZ plus vector R minus rho A rho is equal to 0. So vector R is equal to rho A rho minus ZAZ. This is the magnitude. Root of rho square plus Z square. So dE is equal to rho L into dZ by 4 pi epsilon naught. R square means rho square plus Z square. Unit vector AR is equal to vector R, that is rho A rho minus ZAZ by its magnitude, root of rho square plus Z square. So I can divide this into two components, rho component and minus Z component. So this is a rho component, rho L into rho into dz by 4 pi epsilon naught rho square plus Z square whole to the power of 3 by 2, and this is the Z component. So this is the differential electric field in the rho direction due to a differential length dz. So when I consider the whole line charge extending from minus infinity to plus infinity, what is the total rho component of electric field? I need to integrate this. Okay. So rho L into rho by 4 pi epsilon naught integral minus rho to rho, limits of integration, dz divided by root of rho square plus Z square whole to the power of 3 by 2. Of course, there are several ways of doing this integration. One way is, suppose if I define this angle as theta, what is tan theta? Z by rho. Z by rho. So what is Z? Rho tan theta. So dz would be rho into secant square theta d theta. Dz would be rho secant square theta d theta. Now when z is equal to minus infinity, what is theta? Minus pi by 2. When z is plus infinity, what is theta? Plus pi by 2. So when you convert this dz in terms of rho, in terms of theta, so rho L into rho by 4 pi epsilon naught dz rho secant square theta d theta by rho square plus Z square is what? Rho square secant square theta whole to the power of 3 by 2. So rho cube secant cube theta. So finally, the rho component is rho L by 2 pi epsilon naught rho A rho. On the same lines, if you find out what is the total Z component, you can see that the total Z component is becoming 0. Okay. So the total electric field is given by rho L by 2 pi epsilon naught rho A rho. Now let us do one problem. On the line described by x is equal to 2 meters, y is equal to minus 4 meters, there is a uniform charge distribution of density 20 nanocoulombs per meter. Determine the electric field at minus 2, minus 1, 4. So the line charge density is 20 nanocoulombs per meter. Because the length is not given, you can take it as infinite length line charge. That line charge is obtained as the intersection of x is equal to 2, y is equal to minus 4. So intersection of x is equal to constant, y is equal to constant means it is a line parallel to z axis. So the line charge is parallel to z axis. X is equal to 2, y is equal to minus 4. So this is x is equal to 2, this y is equal to minus 4. So this is the line charge. This is the line charge. Here you have infinite length line charge. Because the length is not given, you can take it as infinite length line charge. So once it is an infinite length line charge, what is the expression for the electric field intensity? Rho L by 2 pi epsilon naught rho A rho. What is rho? The perpendicular distance from point P on to this line charge. So that point is having a coordinates of minus 2, minus 1 and 4. So the perpendicular distance from point P on to this line charge, this is defined as rho. Okay. So if you know the coordinates of this point, then x1, y1, z1, x2, y2, z2, you know how to write the vector rho x2 minus x1, ax plus y2 minus y1, ay plus z2 minus z1, az. So how do you get the coordinates of this point? Because this line is obtained, the line charge is obtained as the intersection of x is equal to 2 and y is equal to minus 4. Every point along this line charge, the x coordinate is constant 2, y coordinate is a constant minus 4. Only z coordinate changes from minus infinity to plus infinity when you go from one point to another point along the line. So how do you find this z coordinate? Because this rho is perpendicular distance from point to the line charge. So if this line is perpendicular to the line charge, z coordinate of these 2 points should be same. So because the z coordinate of point P is 4, here the z coordinate has to be 4. So once we know the coordinates of this point as 2, minus 4 and 4, okay, then rho is equal to minus 2 minus 2. So minus 4ax plus minus 1 plus 4. So plus 3ay. Then the magnitude is 5. Electric field intensity is 20 nanocoulombs rho L. Rho L means 20 nanocoulombs by 2 pi epsilon naught. 1 by 4 pi epsilon naught is 18 into 10 power 9. So 1 by 2 pi epsilon naught is 18 into 10 to the power of 9 by magnitude of rho it is 5. A rho is equal to minus 4ax plus 3a by 5. So ultimately this is what we have got. Minus 57.6 ax plus 43.2 ay.